So I'll be talking about reinforcement learning approach for ABR algorithms. Brief about me, I've been working with the JavaScript for about 6-7 years. More recently, I've been doing mostly ABR and machine learning with JavaScript. So here's what I have planned for you guys. So first, I'll briefly talk about what is ABR and why we wanted to do a machine learning-based approach for it. And of course, how it all fits together. And then I'll walk you through the challenges and our experiences of taking this approach for our production users. So Hotstar, it's a classic sort of streaming company where you have HLS dash streams, there's all types of devices, there's ads and ads-free experience, and of course there's sports, live sports, and everything. So along with content, probably the next most important thing is the playback experience. And if you're looking at improving that thing, there's probably 3 broad areas where you can work on. Encoding is about how best you can compress. I think a lot of folks have talked about it today. And delivery is how efficiently you can deliver it. And the rest is about the player experience. And if you're looking at how you can improve the player experience, these are probably the primary metrics you look at. So there's error rate, and there's start lag, like how long it takes to start the playback. And there's, of course, rebuffer, quality, and so on. So most of these are dependent on the ABR algorithm, which is driving the player. So what is ABR? The problem is fairly straightforward. You have your streams, multiple streams, and you split it into chunks. And at each iteration, you just want to pick the best. Now, the definition of best is about how you want to optimize your QOE goals. So that could vary. And just one thing to remember is that there are competing goals here, because highest quality every time can cause increase in probability of rebuffers. So that's where the challenges of an ABR algorithm come in. And so how is it being solved for the last 5 or 10 years now? So there's 2 main approaches that are out there. One is about throughput estimation, where you're trying to estimate your throughput for the next few seconds based on what you've seen in the past. And then is about the next set of algorithms are based on buffer-based, where it's about buffer as your control parameter, and you build your algorithm around it. And then there's, of course, a hybrid of it. But there's one common denominator on all of these, is that these are all heuristics-based, where some engineer has come up with these heuristics. And with all heuristic systems, they're prone to some bias. So of course, everyone does A/B testing, right? So those bias, there's some scope of normalization there. But still, the whole iteration is like you do an A/B test, and then you fix something based on what you think is the best. So we wanted to look at something like a purely data-driven approach for this. And the reasons were, first of all, we had access to a lot of data. So already there were millions of sessions being logged in every day. And machine learning has evolved quite a bit in the last 5 years, and it has had quite a lot of success in some problems, similar data-driven solutions, so to speak. So, and of course, the developer tools, and especially the Tensorflow tool, you can actually train your model in Python and export it to either JavaScript, or you can run it on Android, iOS. So that seemed like a good idea, and we wanted to give it a shot. So so we started researching about what are the techniques that are out there, and there's one which is about predicting the throughput, and we like the second one better. The second one is this RL-based approach, because this is a really nice paper. There was some research done at MIT, which I'll talk more about their work, but essentially not only they did some research, they open sourced some code as well, and they had some experiments, like in a limited setting, and they had really good results on it. So if you see, the red one is the Pensieve performance as compared to the other algorithms which are out there. And it does quite well. So given all of that, we came up with a master plan. We just wanted to, find one, we wanted to find a model which can work with one specific ladder and try it out in the field, and then we can generalize it to any ladder. So in practice, this is how it turned out. These are the tasks that we needed to perform. Of course, there were some ramp-up time, but there was also a lot of time was spent on the reward function and the training part, which I'll talk more about. And then it was about evaluation. Like, once we have a model, how do we evaluate it? So we built some lab testing tools, and using Chrome Puppeteer, we actually used their API to automate this testing, where you can have your throughput profiles, and you can launch 2 tabs with different algorithms, and then you can gauge your QOE performance out of it. And then, of course, we did A/B testing on it. So what is RL? RL is a technique it's kind of an approximation of dynamic programming, if you guys are familiar with. But essentially, if you have a series of decisions to be made and you're trying to achieve an end goal, it gives you some techniques to find an optimal solution for that. So you're taking an action so that your cumulative sort of reward at each step is maximized or minimized, I guess, if you have negative rewards. So if you can model your problem where you have an agent which is interacting in an environment at any time, it could be, let's say it's in state 0 at time 0. It takes an action, and then it goes to time 1. The environment will give it some reward, and it will go to state S1, and so on. So you'll have these series of tuples of these values. And essentially, you want to maximize your goal, maximize your reward, which is achieved at each point of time. And once you have your problem modeled this way, your goal is to find a policy function, which is out of those actions that are available, what should I pick? So problem now reduces to finding this policy. So how does it fit in our use case? If you see on the left, there's bandwidth and bitrate and buffer, which is our state at any time. On the right, there's available actions, like which bitrate or which resolution you would want to pick. And once you pick something, you get a reward, which has some quantitative value of your quality, and it has a negative penalty for your rebuffers and so on. And this neural network is implementing your policy, which I'll talk more about it. So those are the 5 main things. This is what we use for our state. So you have throughput, download time from. So based on this paper, it tries with like last 8 values or last 16, last 1. We pick the 8th one. So there's throughput, download time, chunk sizes, buffer level, number of chunks remaining, and bitrate of last chunk. Action is simple. Typically on your ladder, you will have maybe 10 levels. So you just which chunk to pick. And this is the reward at each step, and then we accumulate it over the session. So here Rn is the bitrate of chunk n, and Tn is the rebuffering time. So once we have this, right, so this is what our training process will look like. The input to the training will be just the throughput trace. So this, you can either take random samples from your production users, or you can create in the lab. You can create these high variance traces, and once you have lots of those, you give it to the training system, and then what it outputs is that policy function, which you can then deploy on your clients. I'll talk about the training in a bit, but this is the general idea how it will work. So before we go ahead, just a kind of hello world for like data-driven approach to solving these problems. So let's say you want to predict a watch time, and you knew what, like based on your previous user behavior, you know this is how the trend is. So you can come up with an approximation function, and you can come up with like an equation for it. And now, if you know M and B, you can just put in a value of X, and that is all you need, right? And there's some elementary calculus that you can use to achieve those. But the high-level thing is that you come up with a loss function, and so which is your predicted minus actual value, and then using calculus, you can find the value of M and C. This can be extended to like a more generic use case where your X is not one parameter, but it's like a vector. And your f of X, it's not always feasible to just make a linear function out of it. And you can also use it for classification problem where you want to get a probability of your output falling into one of your discrete outputs. So for that, a more sophisticated system is used, but this is also just an approximation function where you have your inputs, and so it's again data-driven approach for solving problems where you have your known inputs and your known outputs, and you can come up with the weights for this neural network, and that's it. So coming back to our original use case, so this is how our problem is set up, where we want to find the policy. So let's assume if you had a particular state and you wanted to know if you take action A, what should be the expected reward after taking that action. So if you have that sort of hash map or some data structure to store that, then your problem is solved. So you can always, at any time you're in some state, you just say, give me the value of action A, action B, and so on, and then you pick the maximum one, and that's it. And how do you create that is using a Bellman equation, which is over there, but the proof is sort of more involved. But for now, assume like this, so you start your Q function or hash table with nothing in it, and then you play a lot of sessions or feed like a lot of episodes to it, and then it will converge to the optimum value using this. And there's an exploitation mode, which is like initially you're taking random actions with some probability so that you don't end up in like a local maxima or a local optimum. So this is all what the algorithm would look like if you were to build up that Q table. But the problem with Q table is it's not scalable, especially if your state space becomes large. So we extend these concepts, and instead of creating a Q table, you create a neural network, which I just talked about. Some of the concepts apply here, where you essentially play something, you build a replay buffer, and then using this equation over there, you come up with the loss function, and then you just reduce this to a regression problem, and you can reuse the techniques that are out there. So this is specifically the algorithm that is used in the paper to find the policy. It has more pieces to it, so if anyone wants to know more about it, you can just Google A3C. I think that should be enough. And it's all done in TensorFlow Python, so the APIs are there. So after that was all the theory that I'll talk about. But after we have the whole model ready, the next step was to integrate it in the player, in the JavaScript player, and we started with HLS.js, which has a straightforward way of doing a custom ABR. And you can use a player API to get the state and then do everything that you need in your model, like state, action, rewards. This is straightforward to achieve those. And we use Tensorflow.js for running the machine learning model itself. So Tensorflow.js, just a few things. It runs on GPU, so it uses WebGL textures for its data structures, and it runs all the operations in parallel on GPU, so your main thread does not get blocked. But there is a caveat that we found recently, that transferring of data from GPU, so GPU has its own memory, right? So That can be a bottleneck sometimes, so you might want to look out for that. And you have to do explicit memory garbage collection in that. So, but this is essentially what the code looks like once you have that model ready. So what were the main challenges? The first one was getting a good reward function. This was the most time-consuming part of this whole thing. The problem we were facing was sometimes the model would converge to like only a couple of outputs and it won't go through the entire ladder. Or sometimes the entropy was really high. With that, I mean that it did not have a high confidence in the output, so it wasn't stable. And sometimes we were seeing that it wasn't working as expected in terms of our QOE equation. So this took a lot of iterations and hit and trial, but eventually we did find a good model in there, so that's all good. And JavaScript export also had some roadblocks because TensorFlow was going through a lot of API changes in the last 6 to 8, or maybe a year. So there were some formats which they used to support, but they stopped supporting it. So, but anyways, we were able to find some, I think 3 months before they had released a version, so that all worked. And we did see an increase in drop frames, and this was, we did some optimizations to reduce the CPU load and the way we were scheduling it. But one thing to remember is that the default mode of Tensorflow.js is WebGL, which is GPU. But I don't think that is required in all cases. So we are yet to run this in A/B test, but when we were doing lab testing, there was like 50% better performance just using CPU alone. So, and lastly, there was some issues with HLS.js when we were integrating it with the custom ABR. The handling for fragment abort, we were kind of buggy there, but I can talk more about it later if somebody is interested, but that's all what we had. And A/B test results, these are the first 3 metrics, so there's more detailed analysis, but this is just a summary. We were able to find a model which could match for these primary metrics. There's slight increase in drop frames, which we are yet to, there's one more thing which at least we want to try, I think which will get some improvement there, but the level changes is still high, so like more upshifts and downshifts are happening as compared to the existing one, which can be driven through the reward function, so we just need to go, just go try more options on the reward function. So overall, this actually works end-to-end. We didn't see any major roadblock. I think it's just about training strategy, like what kind of data you're using. And we still have some guards, which is, so this is not entirely data-driven. There is some heuristics in it. But hopefully, with more rounds of testing, we should be able to get rid of those. So that is it. And some links. So this second link is actually, so they did the same experiment at Facebook, which the original authors of the paper. So they've talked more about that at the second link if somebody's interested. And that is it. Yeah.